All right, let's get started. Hi, come on in. Thanks. You're going to have to squint a little bit more than usual. The fire marshal decided that having a few extra pieces of paper up on the window was putting us all at risk. So we're safe now. The fire marshal has decided that with that much reduction in the paper that we're not all going to burst into flames. All right, so apologies if you can't see the screen. Your homework assignment is due on Thursday, and also on Thursday we're going to have our first exam. Here in this room, it's 75 minutes long, and the equation sheet's already on MU Online if you want to have a look at that. It's inevitable every semester I have students who are asking, like, is the order of the equations on the equation sheet some sort of an indication of what you can expect on the exam? And no, none of that kind of fortune telling based on the equation sheet will ever be successful. And in fact, I haven't put the exam together yet, and so I couldn't even tell you what's going to be on the exam. I'll probably be putting that together tomorrow. So yeah, it's as much as mystery to you as it is to me. But it will be covering classes 1 through 11, so that's chapters 2 and 3 in the book. So any questions related to the announcements before we start talking about stability of floating bodies and just a quick overview of buoyancy? All right. Well, the main idea with buoyancy is that it's related to the volume displaced. And then we can apply it to criteria like the weight of the object and the buoyancy to make decisions like, will a certain object that's in water sink or float? Not every object is in equilibrium. Oftentimes, if it's floating at the surface, then you can maybe, from the image, assume that it's floating, and it'll usually say it in the problem statement. But let's take this one as an example. We have a barrel that's 2 meters in diameter, 180 centimeters long, and it's submerged 5 meters below the surface. Does it matter how deeply submerged it is? No. Why not, Stuart?
Because the wet portion is the same surface.
Right. That's right. And so this is an example of information that sometimes you're given that doesn't actually play into the calculations. Just because a piece of information is given doesn't mean that you have to use it in a problem. So the pressure on the top and the pressure on the bottom are both increasing the deeper it gets, but the difference between the two isn't increasing. And so the only thing that's significant about that depth of 5 meters is that it's below the surface. It's fully submerged. And so I'd like you to calculate two things. First of all, based on the dimensions of it and the fact that it's submerged in water. Does it even say water? No. It's submerged in water. Let's assume it's water. Temperature not specified. Will it sink or will it float? All right, since buoyancy depends on the volume of the barrel, that's where we can begin. It's just for a barrel going to be the area times the length. And so for a circle, the area in terms of d is pi d squared divided by 4. And we multiply it by the length of 1.8 meters since it's 180 centimeters. And so we get the volume, and from that multiply by the unit weight of the liquid that's being pushed out of the way by the barrel, which in this case we're assuming is water. And so we get a buoyant force of 55,000 newtons. That's pushing the barrel up. Now the barrel itself has weight based on its mass, and so we can calculate the weight. It's just the 1,600 kilograms multiplied by g. So the weight of the barrel is less than the buoyant force, so that's going to mean that the buoyant force is pushing the barrel upward. Another way to looking at it is just looking at the unit weight of the barrel relative to the unit weight of water. Kind of like how sometimes we consider the density of oil, and we know from the density that the oil is going to float on top of the water, just if the density of something is less than the density of water. And so in this case, the unit weight, which is related to density, is less than the density of water, or less than the unit weight of water. Now, one other idea occurred to me as I was wandering around, and that is, so does what we've just done here tell us how quickly the barrel is rising to the surface? Because what we have is a difference in forces, right? We've got, yeah, I heard somebody say what the direction I'm headed in. So the buoyant force is 55.5 kilonewtons up. The weight of the object is 15.7 kilonewtons. And so, we have this equation, the sum of the forces is equal to ma. The sum of the forces here is that there's a net force upward. So is it just that easy? Could we use this to find out how quickly the barrel is accelerating upward? It depends. This assumes that there is no friction. And so as soon as that barrel starts to move upward through the water, think about viscosity and think about the resistance that the barrel would face. And so it's not going to be accelerating in a vacuum. This approach would work if it was accelerating without any resistance. But in reality, the faster the barrel is moving, the greater the drag forces. And so just as a preview of where you'll actually get to when you take the wastewater course, or hopefully by the time it comes around for you to take it, it'll be a different environmental engineering course. Regardless, you'll learn about the acceleration of particles through fluids, and that's important in water treatment. So we can't just say we know how quickly it's accelerating because of the drag forces, which are gradually increasing as a function of the barrel speed. But we do know that it's going to float until it reaches equilibrium. And if we wanted to, we could even calculate how it's going to be floating at the surface, although that would be a little bit tricky because of the shape of the circle. All right, so any questions on the calculations that you did to determine whether it would sink or float? Here's a related homework problem. And what we have here is a side view. And I think probably the number one thing that students struggle with on this problem is just visualizing what this object even looks like. What it is it's like a superstructure above the water and then 4 barrels beneath the water. Let me draw an overhead view of what it looks like. All right, so then there's sort of like connecting these 4 barrels. So what you're looking at here on the screen is viewing this from the side. If we view it from above, we can see that there's 4 of these barrels. And so what it is, what's keeping this afloat is the fact that these barrels are partly submerged. We know the diameter of the barrels. We know, you can see from the drawing here, that the platform itself, the superstructure above the barrels, has a weight of 30 kilonewtons. And then these barrels themselves, they have a weight of 1 kilonewton per meter. And so if I was going to draw one of the barrels, this is a side view of it, 1 meter is equal to 1 kilonewton. That's how much the barrels themselves weigh. So what the problem is asking, see the L here? They want to know how deeply submerged the barrels are. And from that, what is L? Yeah, how long do the barrels have to be? If you want to have 1 meter of clearance, you want to be up above the waves a little bit so you don't get splashed or whatever, I guess. So you're above the water surface by 1 meter. So how much submergence do you need below the water surface to keep this in equilibrium so that you have enough buoyancy to overcome the weight of the object, so that the buoyant force and the weight, the overall weight, is in equilibrium? All right, so this is another one of those vertical force balance problems. You've got the forces up, which are buoyancy. You've got the forces down, which is the combined weight of the barrels and the superstructure together. So I wanted to mention this problem since it's due on Thursday, and it's always a little bit tough to see it as like a 4-barrel object. It says it in the problem statement, but the picture doesn't make that immediately clear. Now that you've seen the picture, any questions about it? All right. Well, Let's look at another picture. I'll dim the light so you can see what's going on here. All right, sailing. And why are they sitting on the edge? Any guesses? It looks like it's about to tip over, right? And so what does sitting on that edge instead of sitting on the other edge accomplish, other than keeping their feet dry? If they were sitting on the other edge, they'd probably getting splashed. So why is it helpful for them to sit on that side? Counterbalancing, right. They have weight, and so if they sit on that edge, the boat won't tip over as much. And besides, it won't really like sink if it tips over, but the sails, if it's over on its side, they're not catching as much wind as if the sail is upright. So that's part of the reason. So what we're going to be talking about today is stability of floating bodies. You know, whether boats are going to tip over or whether they're stable. And consider these two cylindrical objects. On the left is a submarine, and on the right is a wooden log the little boy is balancing on. And so they've got some similarities. The object on the left and the object on the right, they're both floating, they're both cylindrical, they both have people standing on top. The one on the right doesn't have nuclear missiles in it. The one on the left does. But that's not the main reason why the sailors aren't dancing trying to keep their balance like the kid on the log. So any guess why the sailors aren't having trouble keeping their balance, and why doesn't that submarine just tip over? Like, it's top heavy, right? Look at this. This conning tower, as it's called, there isn't one of those on the bottom. So it seems like, just based on the picture, it'd be kind of top heavy and prone to tipping over. Center of gravity, yeah. So not pictured is probably ballast at the bottom of the submarine. You know, a heavy concentration of weight at the bottom of the submarine is going to make it stable. So here is a conceptual representation of that sort of approach, where you can see from the weighting that what they've done is they've moved G, which is the center of mass, or the center of gravity, below the center of buoyancy. So the letter C means center of buoyancy. And what determines the center of buoyancy and where it's located? The volume and the shape. The shape of the thing that's pushing water out of the way. So remember, buoyancy is all about water being displaced. And we've said several times the magnitude of the buoyancy is equal to the weight of the water displaced. And so it turns out that the location of the buoyancy is also guided by the water that's been pushed out of the way. And so here, if it's a circular shape on the exterior, then the center of buoyancy is the center of area of a circle. And so the center of area of a circle is in the middle of the circle. So that's why C is in the middle, is because that is the centroid of the water that got pushed out of the way. But the center of gravity is more about where is the average mass of not only the outside material, but all of the material on the inside of that water that's being pushed out of the way. So C, center of buoyancy, G, center of gravity. And you can see what both of those are related to. So this is stable. Picture A is stable. And why is it stable? If you tipped it, what would happen? Like if I took that weight and I rotated it so that the weight was at the top, when I say that it's stable, what do you think that that means? It's going to go back to the original position, right? It's always going to have one preferred location with the weight at the bottom. If you roll it over, it will right itself. That's what we're going to call stable, is that, I mean, that doesn't mean it never can be tipped. All it takes is, you know, a certain force to rotate it out of its stable position, but it'll go back to stability. B is neutral. So neutrally stable. What that means is it's not going to right itself necessarily, because the center of gravity and the center of buoyancy are in the same location, but Object C kind of illustrates what would happen from a vector standpoint if you did move the weight into its unstable position. So C, this is unstable as pictured, but because of the righting couple, here in italics, it's called a righting couple. That means that the direction of those two vectors is such that it's going to rotate the bottom, which is where the weight is located, back to the lowest part. So think about if you were going to put your fingers, your left finger on C and your right finger on G, and then push in the direction of the arrows. So you're putting it on a piece of paper, and your left hand is going up and your right hand is going down. That's going to rotate the piece of paper. And so those forces are acting just in the direction that's indicated. The buoyant force is acting up. The gravitational force is acting down. That's what these arrows represent, is the forces and their direction. So any questions so far about this conceptual representation? All right, so let's get a little bit more realistic with a depiction of a boat. So what does C stand for? Center of buoyancy, or center of volume, and it's dependent on the water that got pushed out of the way. So where it's located is dependent on the shape underneath the water line. C doesn't know and doesn't care what's above the water line, because what above the water line has no effect on buoyancy, not directly. I mean, if it's really heavy, then it'll push the boat deeper into the water. But the direct location of C and the magnitude of C is all about the shape of what's under the water and where the water is being displaced. G, again, center of gravity, center of mass. Now, G is dependent on what's above the water line. And so if we have a lot of mass above the water line, then that would bring G higher. Like if we were going to stack this boat with those containers that you see coming off of ships. So the buoyant forces act up, gravitational forces act down, but what if the ship tips over? Maybe because of waves or wind, or because it's been loaded incorrectly. We've got some different letters on the screen here. Let's first of all dissect what all these different letters are. What does A and D represent? A and D is where the water line used to be before it tipped over. So that's just reminding us of the previous water line. B and E is just sort of showing us where the water line intersects the ship. And so B and E are the new water line when the ship tips over. The location of C has changed, and this is really important. C on the left picture was directly under G, but now C is to the right of G. Now C is the center of buoyancy, so why did that buoyant force location shift to the right? Can you look at the picture and, yeah, go ahead. The position of the water changed. What do you mean? Okay. There's more volume displaced on the right side. So if you look at the shape of that ship, it seems like the center of area for the submerged portion of the ship is further to the right, because they kind of design ship hulls partly for that reason, so that if it tips over, now you've got more submerged on the right than you do on the left. Okay. So this can right itself automatically. This ship doesn't need thrusters or whatever to tip it back into place, because we can do the same thing with our fingers that we did in the previous example. You put your left finger on G, your right finger on C, and then you rotate it according to the direction indicated by the arrows. And so that righting couple that we saw in the previous cylindrical shape also exists for a more complex ship shape. M is called the metacenter. And the metacenter is what C is pointing to at all times. So if we tipped it over a little more, if we tipped the ship over a little more, then C would shift further to the right, but it would still be pointing towards the metacenter. So the metacenter is kind of like an axis of rotation for the ship, that the center of buoyancy is always pointing towards. Okay, so if the ship tips, then the C, the center of buoyancy, moves, and the metacenter is the point of intersection of all the lines of action from the buoyant force. In other words, C points towards the metacenter. And this is stable because of the righting couple. If the ship tips a little bit, if it heels, then the center of buoyancy shift is just going to push the boat right back into its original position. Now, if there's lots of waves and lots of wind, then it's going to be rocking back and forth, making us all really sick. So they do have thrusters, like to sort of keep it from tipping over on cruise ships, just for the comfort of passengers, but they're not necessary to keep the boat from sinking. So there are a number of calculations that we can do about all this, and ships are designed not to tip over, and there is kind of a numerical way for us to analyze the risk of whether a ship will tip over or not. The criteria that we can apply is that if M is above G, so if the metacenter is located higher than the center of gravity, then the object will be stable. So that's our criteria, if M is above G. So if I put a lot more containers on top of this ship, what would that do to the location of G? It would move it up. Why would it move it up? Why would it move the center of gravity up if I loaded more and more cargo on top of the ship? More top heavy, and there is some ballast at the bottom of the ship, but G is just kind of like the average of where is the mass distributed in the ship. And so the more cargo you put up high, away from the waterline, what you're doing is you're raising the center of gravity and getting it closer and closer to the metacenter. So if the center of gravity is at the metacenter or higher, then it's so top heavy that it's going to tip over. And the righting couple won't have the effect of bringing it back into its neutral position. So if G is above M, then the ship tips over. And that's the analysis that you need to do. Now, in performing that analysis, one of the things we have to come back to is the idea of area moment of inertia. And for a ship like this is a barge. It just looks like it's rocks. It would be more fun if it was a garbage barge, because that kind of rhymes a little bit, garbage barge. There's always like famous movies of like cars going off of a bridge and landing on the garbage barge. But the garbage barge never tips over because, it's stability of floating bodies and all that. When you calculate the area moment of inertia, you will assign the parameter B to the shorter dimension. So this is rectangular, so you'll notice in area moment of inertia here, you're cubing one of the parameters, and one of them you're just taking to the first power. And so, why is that? It's because it's more risky for it to tip over about this axis. If you think about what's the greater risk, that it's going to tip over and sink this way or this way. And so you cube the critical parameter, I guess you could say, is the shorter of the two dimensions. And that's why on a boat, it rocks side to side more than it does front to back, is because the side to side motion is, the boats are less wide than they are long. So once you have the area moment of inertia for a boat, that's a top view thing. You get it from the shape that is formed at the water line. And so, in other words, the top view defines the shape of the water line. Here's the formula for calculating GM. And GM is the distance, how far apart the center of gravity and the metacenter are. And so you have the area moment of inertia, I, divided by the volume, the submerged volume. So that would be the volume that's generating buoyancy. So the bigger this first parameter is, the more stable the object is going to be. Because what we want is we want a GM that's positive. If you have a GM that's negative, that means it's going to tip over and it's not going to be stable. And so the thing that promotes an unstable situation is when you have a big CG. And so you look at CG is just the distance between the center of gravity and the center of buoyancy. And so, for example, loading a lot of cargo high on the ship is going to raise the center of gravity. And so that promotes instability. Well, what promotes stability? A really wide barge. The wider it is, the less likely it is to tip over because we're going to have a large area moment of inertia. So does a big I divided by V promote stability or instability? Well, it promotes stability because it's the first of the two parameters, and when it's positive is when we have it stable. When it's negative, we have unstable. All right. Here is an example. Now, the last couple of in-class exercises we've done, I've collected from you and given you points for. But this one I'm going to leave with you so you have access to it as you do the homework, because there's a homework assignment that's closely related to this problem, and I want you to have this available as a resource. So you don't have to be like super neat like you do when you're giving something to me, but still, be super neat for your own sake and your own benefit. I have a series of questions that I'm asking in certain order that I think will make it easy for you to understand whether this particular barge is going to float or whether it's going to tip over and sink. All right. Everybody get a copy of that handout? Thank you. Two more? Here you go. All right. So as always, you're free to collaborate with your classmates on this one. And we'll take a look at the solution in just a moment. All right, so the first thing we need to know is, what does it say? The weight. And so the weight of the object is just the mass multiplied by g. And so about 1.77 meganewtons. And because it's floating in equilibrium, then that means that the buoyant force and the weight are equal. And so the weight and the buoyant force are the same. And so from that, saying that the buoyant force is equal to this quantity, then we can solve for the submerged depth. So we know the unit weight of water. The only parameter that isn't known is the depth, because the width and the length are fixed. It's just how deeply that's going to be sitting in the water. And so from that, we can find D is 1.978. And as I walked around, it seemed like everyone was sort of honing in on that same value. Okay, the thing to look at now for the area moment of inertia is what is A and what is B. And its axis of rotation, its likely axis of rotation is going to be, because of this 6 meters being the narrower of the two dimensions, it's more likely to tip this way. So we're going to cube that parameter and then just take A, which is the length, to the 1 power. So here we get I for the area moment of inertia. The submerged depth. The next thing is to find the center of buoyancy. And so the center of buoyancy, we have to take that depth, the submerged depth of 1.978, and divide it by 2, because that will tell us where C is. C is half the distance from the bottom to the waterline. So halfway is where the center of buoyancy is. And then we know how deeply it's submerged, and we also know the overall height of that object. It's 2.44. And so that allows us to calculate from the water line up to G. And you add those two lengths together, and that's where you get the CG distance, 1.451. And then from there, it's just substituting everything in. And the criteria is if you have a positive GM, then that means it's stable. And that's what this one is. This is stable, just barely stable, though. It would be pretty easy to make some changes to this barge, and then it's at risk of tipping over. If it was negative, then it would be unstable, and then that's the one that's at the first sign of a wave, wind, or someone walking around on the deck, it's just going to tip right over. All right. Any questions related to this? Okay. I think I had a second part of the problem where I asked how wide would it have to be for it to be unstable? And so I went through that process, and I found that all we would have to do is make it a width of 5.87 instead of 6, and then that would be narrow enough that it would now be unstable. So that's one of the things you could do to make it unstable. Stuart?
B is going below the water line.
That's right, yeah. All right. So that's the end of the material that's going to be included on the exam. I want to go over just an overview, getting ready for the exam. Sometimes students ask,